Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start the lecture 4 of our resonance chapter. So today we will discuss about parallel resonance circuit. So for a parallel resonance circuit we will choose current source. Why? Because current division happens, right? In case of series we used voltage because voltage division was happening between RLC. Now I want the current division because resonance will happening through the current source. That's why. Okay. So to divide the current, that's why we are using the current source. Okay, so in this case what needs to happen, again my circuit has to be purely resistive. My circuit has to be purely resistive. So what I can do is I can now calculate with respect to admittance. I will take help of admittance because in I have my circuit is parallel, so admittance will be the easier way to calculate everything. So in parallel, admittance is added. So what is the admittance of this R? It is 1 by R. What is the admittance of this inductance XL? It is 1 by XL. 1 by JXL. What is the admittance of this capacitance? It is 1 by minus JXC. Okay. It is just the inverse of the reactance. So I can directly say my Y seen from the source will be 1 by R, then plus J XC minus 1 by XL. Okay, so this will be equals to Y 1 by R. Now what do we have to make? We have to make the imaginary part of the admittance to be 0 because I want my circuit to be totally real. Then only the current and voltages will be in phase. This voltage across the resistor and the current that will flow, current that will come, right? This supply voltage and current, both of them will be in the same phase. I want it to be purely resistive circuit. So this will be purely resistive. So this will be 1 by R. That is imaginary part is 0. That is 1 by XC minus 1 by XL is equals to 0. So same condition we get, XL is equals to XC. From here again omega naught L will be equals to 1 by omega naught C. Okay, so this will be equals to omega naught whole square equals to 1 by LC, omega naught equals to 1 by under root LC. Okay, so that is what we get for a parallel resonance circuit. This is the condition basically. So this is one of the way to solve. What is the other way? Other way is to draw the phasor diagram. I want my circuit to be purely resistive. So I can, as it is a parallel circuit, I will first plot the voltage. So voltage will be somewhere here, correct? Not voltage, sorry. Let me plot the this current IR, right? Let me first plot the voltage. Basically voltage is here. Okay, voltage is here. What about the current IR? Current IR is in the same phase as the voltage V because it is just parallel, right? Because voltage is same across everything. So current across the resistor and voltage across the resistor has to have the same phase. Okay, they don't have any phase difference. So that's why it will be in the same phase. What about the current IL? Current IL will, this voltage is same, right? This voltage is same as V, will what? Lag. In inductance, current lags. So here the current will simply lag. Okay, it will lag. And for capacitance, the current leads. For capacitance, the current leads basically. Okay, so now what I can see is this will be now at resonance. What is happening? my voltage, what is overall current? Overall current is the sum of these, right? Sum of all these three vectors or phases. So of course I want my overall current to be in the phase of voltage. I don't want any phase difference between voltage and the current, overall current. This is the current I don't want that. So of course I will want these things to cancel each other out. I will want the current, capacitor current and the inductance current to cancel each other out. So ultimately my overall current will be equals to IR only. This will be my I, that is same as IR. Okay, I will be equals to IR. So basically I can write like this was the phasor representation diagrammatically. So I can write I equals to IR plus J IC, because capacitor current will lead the reference voltage, that's why it is with plus J, and minus IL because inductor current will lag the reference voltage. Okay. So that is the case over here. Now again I want it to be purely resistive, right? So I want I to be equals to IR. So again imaginary of current also you can make it equal to 0, or from here directly you can get the admittance, that why admittance is added. So basically what is I is simply what, overall admittance into V, right? I is the overall admittance into V. What is I is equals to admittance into V. What is Z is equals to V by I, correct? So Y will be I by V, just the reciprocal. So same as well, I replace I with Y into V, and this will be IR. So I will replace this with its own conductance, that is 1 by R into V plus J. I will replace this IC with its own conductance and voltage. Voltage is same. So IC into XC. IC into XC minus, not IC into XC, sorry, into sorry V into 1 by XC basically, and this will be V into 1 by XL. Okay, so overall you see that ultimately V will cancel out because V is common. It will be equals to 1 by R plus 1 by XC minus 1 by XL. Okay, so like this also you can prove always. So the resonant frequency is same, it will not change obviously. Resonant frequency omega naught will be 1 by under root LC. Okay, for a standard parallel RLC circuit, for a non-standard circuit we will derive the expression for non-standard circuit. Okay, so I hope you have understood the point. Now few important points I wanted to clear. What is the voltage at resonance? Okay, what is the voltage at resonance? So voltage at resonance will be what? V will be equals to admittance into not this, sorry, current at resonance is admittance into voltage, correct? Admittance into voltage is the current at resonance. So I don't know about voltage, I know about admittance. So my voltage will be current by admittance. So my current is some constant value current only. Okay, so I can discuss about the magnitude of the voltage. Magnitude of the voltage will be magnitude of the current divided by the, this will be Y, sorry, by Y, right? So what is the magnitude of Y? Magnitude of Y is simple, 1 by R whole square plus 1 by XC minus 1 by XL whole square. Okay, this is the magnitude of voltage basically. Okay, you have understood this very basic point. So now can you tell me at what frequency the circuit is behaving? So again remember one point, in series, right, if I have this impedance, let's say this impedance I have, or let me choose a simple resistor only, R1 R2. Okay, in series let's say R1 is 10 ohms and R2 is 10 this much ohms, right? So what is the equivalent? Equivalent is almost equals to R2. So in series, the higher resistance dominates. So I will write in series, higher resistance dominates. Okay. What about parallel? So in parallel I have this resistor R1, and then I have this resistor R2. Now let's say this R1 is again same, R1 is 10 ohms, R2 is 10 this much ohms, right? Which will dominate? Now you will of course say that sir this one will dominate. You can find out the equivalent. You will see almost it is this combination is almost equals to R1, that is 10 ohms. So in parallel the lower resistance dominate. Okay. If I want to say this in terms of conductance, how can I say? The higher conductance dominates. So this has higher conductance, right? This Y1 is higher. Y1 is higher than Y2. So which one has higher conductance, that will dominate. Got it? Great. So same thing we will do here. We will discuss about conductance, right? So what is my capacitive conductance? It is 1 by XC. It is XC is 1 by omega C. So it will be omega C. And what is my inductive susceptance? It is 1 by XL, and XL is omega L. So it will be 1 by omega L. Okay, it will be 1 by omega L. So now if I say for low values of omega, right, for omega less than omega naught, which one will dominate? For omega less than omega naught, let's take a number, omega is 0.1. So let us assume that L is same as C. So this will be this will be like BC will be 0.1 C, let's assume C to be 1, okay, and my BL will be 1 by 0.1. So of course this is 10. So BL is higher. So what did I tell you? Whose susceptance will be higher, that one will dominate. So now it is different, right? Previously, if you remember, for series resonant circuit, if my frequency was less than the resonant frequency, it was capacitive. Now it will be inductive. Why? Because my susceptance is lower, BL, so not lower, higher. BL is greater than BC. At omega equals to omega naught, of course, BL and BC are same. It is resistive. At BL is equals to BC. Okay, and at omega greater than omega naught, omega greater than omega naught, omega greater than omega naught, what is happening? My circuit is capacitive. I can prove it to you as well. If omega is very high, right, let's assume omega to be 1000. So if it is 1000, right, this will be 1 by 1000 and this will be 1000 into C. So of course which one will be greater? This will be 0.001, this will be 1000 times something, right? So of course your BC will be greater than BL. Your BC will be greater than BL. Okay, so it will behave as capacitive. So this is the graph. Basically I will plot the graph as well. I will draw the graph as well. Let me delete these things. Yeah, here is the graph, right? So basically the conductance is constant. It is 1 by R. It does not depend on frequency. The susceptance, capacitive susceptance is linear because it is omega C, and the inductive susceptance is hyperbola, just the reverse, right? So if I combine all of this, obviously it will dominate first. So that's why okay, this is negative. So if I am subtracting this, right, because this is getting subtracted because it is BL minus BC, it is BL minus BC. If you see in the formula, this is BC minus BL, right, not BL minus BC, BC minus BL. So this will be negative. So this is the negative, this is minus BL basically. Minus BL, and this is BC. Okay, so what I can say is uh, what I can say is now if I add all these three graphs, if I add all these three graphs, of course this one will dominate because anyways I'm squaring it. So this, right, this, what is the plot? This plot is the admittance plot, right? Admittance plot. Anyways I'm squaring it, so it does not matter if minus BL or plus BL. Ultimately if I'm squaring it, it will become something positive, very huge positive number. But this will be lagging here in this region, it will be lagging, okay, in this whole region. It will be lagging. In this whole region it will be leading, okay. So yeah, that is what the important point that I wanted to specify. These are the regions, these are the graph, okay. I hope you understand. This is the admittance graph basically. So admittance, this will be dominating initially, BL will be dominating, then obviously admittance will reduce to minimum. Because why? Because if you see the admittance formula, right, admittance is what? Admittance, I've written it over here, right? So it is like, oh, I'm really sorry, I forgot to write a G over here. So what is the magnitude of admittance? Magnitude of admittance, if you see, is 1 by R whole square plus 1 by xc minus 1 by xl whole square whole under root 2, okay. Whole under 2, okay. So yeah, this is the case here. So what I can say is basically what I can comment is if I see that obviously admittance, right, will always be something more than 1 by R. Admittance will always be something more than 1 by R because it will always be something non-zero, and if I am squaring it then adding it, of course it will be something more than 1 by R. For just one frequency, when this two will be equal, this will be totally zero, vanished, then only it will be 1 by R. So it is minimum at omega equals to omega naught. That's why it is 1 by R here. The value is 1 by R, the magnitude of the admittance, okay. So yeah, I hope you have understood this point. So same thing we have done here. So initially it is lagging power factor, then it is leading. As it is lagging, the angle will be positive. Impedance, I'm talking about the impedance angle, okay. I'm not talking about the admittance angle. The admittance angle will be negative. Why? Because it is the inverse of the impedance, that is why. So impedance angle is what? Impedance angle is theta v minus theta I. Admittance angle is what? Admittance angle is theta I minus theta v, okay. This is the impedance angle and this is the admittance angle, that's it. So this is the graph. You can intuitively understand this as well. So let me choose very low frequency, omega equals to 0. If I choose omega equal to 0, what will happen? The parallel RLC circuit, this will provide short circuit, this will be open circuit at omega equal to 0. So of course we ignore the open circuit in parallel, right? So it will, all of the current will flow through the inductor, hence it will behave as a purely inductive circuit. So that's why omega less than omega naught, it behaves as a lagging circuit, okay. At omega equals to infinity, what happens? This will provide infinite impedance, so I can ignore this. This will provide zero impedance. So again, all of the current will flow through the capacitor. So circuit will behave as a capacitive circuit. So it will be leading power factor. That's why it is written here. So in this region, what is happening? In this region, basically the what can I say? In this region, basically my what I was commenting, I forgot. Oh yeah, so capacitor is open circuit. Capacitor is open circuit. Okay, and in this region, the inductor is open circuit. Okay. So these things you have to like keep in mind. C is open circuit here and L is open circuit here. Okay, so these are the few things we are going fast because we already know all the phenomena, all the things. So whatever I have told you, the summary is like written here properly. Okay, so yeah, let us discuss about admittance a bit more. So what is the admittance angle basically? It's like I forgot to derive the admittance angle. So admittance angle will be what? Admittance is 1 by r plus j 1 by xc minus 1 by xl. So angle, admittance angle will be tan inverse of 1 by xc depending on the sign by 1 by, this will be L actually, properly this will be L, by 1 by xl divided by 1 by r. Okay, so this is the admittance angle basically. Got it? Now if I I have already discussed about the the magnitude, and this is the admittance angle. Like if you want to simplify, right, you can simplify here. You can replace xc with omega c. So this will be omega c minus 1 by omega l divided by 1 by r basically. Okay, so from there you can find out the different results, different values of admittance. Okay, so what is happening to the current basically? So what is the current or the voltage? Let's discuss about the voltage, right? So the voltage is I upon y, correct? This is my voltage. So at resonance the y is minimum, magnitude of admittance is minimum, correct? Okay, so this v is equals to magnitude of y divided by magnitude of y. So my voltage, hence my voltage will be maximum. So it magnifies the voltage basically. At resonance my voltage is maximum. Previously if you remember, at resonance my current was maximum for series RLC circuit. Here the voltage will be maximum. So this thing you have to keep in mind, your voltage will be maximum at resonance. Okay, yeah. So these are the few things, and the power factor at resonance is 1 basically. It is purely resistive circuit. This you already know. The vectors, the IR, IL plus IC capacitor current will be 0. The IR, I input current will be equals to the resistor current. It will be in the same phase. Okay, these things you already know about these things. Okay, so I think few graphs are here, so I want to show you few graphs. These are the graphs, right? So voltage is maximum at resonance, and of course the voltage and the current across the resistor, this is the not the overall current. Overall current is constant, right? It is Im sin omega t, magnitude is constant. Im sin omega t, magnitude is constant, but this is the resistor current. So of course resistor, right, voltage is same across the whole circuit, so voltage and resistor will be proportional to each other. So I can directly say that they will be proportional. So current across the resistor will be maximum at resonance. So this also I can conclude that voltage is maximum, hence not the overall current, I am talking about the current across the resistor. The current across resistor will be maximum current through, it's better to write current through at resonance basically. This is also the same thing, IR will be maximum. Okay, so these are few conclusions that I wanted to say. So of course like same thing only here, again it will behave as a lagging circuit, here it will behave as a leading circuit. Okay, this is the graph basically, and of course this is not symmetrical. Again I will have a lower and higher 3 dB frequency. Okay, that will be there. Obviously these are my half power points. What is half power points have been taught to you in the previous lectures. These are my half power points basically, where my voltage will be 1 by root 2 times of the maximum voltage. Okay, so this is the case, and current is here. Yeah, these are few things, and these are the, like, whatever I have explained, these are written over there. Okay, whatever I have explained, these are written. Main point is, if the current is maximum, right, then current across the resistor is maximum, then the power at this point, power will also be the maximum. Power dissipation will also be the maximum, because power is dissipated only in the resistor. If the current is maximum, then the power also will be maximum. Okay, these are the few things, few points whichever I have discussed, those are written over here. You can go through this. Okay, these are the half power points. Okay, you can go through this. Now we will derive for the half power point basically. So I know that the what is the magnitude of the voltage? Magnitude of the voltage is magnitude of the current divided by under root 1 by r square 1 by xc minus 1 by xl whole square. Okay, so what I can comment is that what I can comment is that basically what is the maximum voltage? Vmax is what? Vmax is when these two are equal to each other, that means they will cancel each other out. So ultimately Vmax will be magnitude of I into R. This will be the Vmax. So I need the 70.7%, that is Vmax by root 2. At what frequency this happens? That is magnitude of I into R divided by root 2. That is equals to basically magnitude of I R divided by root 2, that is equals to the frequency, right, at which this is happening. I into R, I divided by 1 by R square plus what is xc? Xc is omega, let's write omega into C minus 1 by omega into L whole square. So I, magnitude of I will get cancelled. If I square on both sides, this will be 1 by R square plus omega C by omega L whole square 2 by R square. Okay, so I can directly say that my omega C minus omega L whole square equals to 1 by R square. So I can directly say that my omega C minus omega L will be plus minus 1 by R. Correct? I cannot simply just ignore the, like, negative sign, right? We have to take both signs. So there are two things here. So of course, if omega C 1 omega C minus 1 by omega L is positive, that means it is what? It is capacitive in nature. It is capacitive in nature. So it will be above the resonant frequency. So if this value omega is equals to omega H into C minus 1 by omega H into L, it will be capacitive in nature. Hence it will be positive, because this quantity will be greater than this quantity. If this is greater, obviously it is capacitive in nature. So it is leading power factor. That's why it is omega H. Okay, and if it is omega L, that is it is less than omega naught, so it is lagging power factor. So omega L into C will be lower than the 1 by omega L into L basically. So this will be minus 1 by R. So this will be lagging power factor. Okay, so This is below resonant frequency, sorry, this is above resonant frequency, and this is below resonant frequency. Okay, so from here you can directly find out the values of omega h and omega l. So let's first find out the omega h. Again, it is a quadratic equation, so this will be omega h whole square minus 1 by r c, okay, 1 by rc, and it will be okay, not omega h also will be there, right? Omega h by rc, so this will be here only. And this will be negative, right? This will come here, this will be also negative, so this will be minus okay, I am multiplying by omega h, yeah, minus 1 by lc, yes, c will get divided, yes, okay, equal to 0. So this will be minus of b, that is 1 by rc, plus minus b square, that is 1 by rc whole square, minus 4ac, 4 by under root lc, divided by 2a. This is my omega h basically. Of course I will ignore the negative sign. If I take the negative sign, right, okay, minus 4ac, right, minus 4ac, this will be plus only, minus minus will become plus. So if I take the negative sign, of course this will be negative, and omega h cannot be negative, omega h has to be positive. So omega h is equals to 1 by rc, 1 by 2 rc, plus minus this plus this can be written 1 by, if 2 is going inside, 1 by 2 rc whole square plus 1 by lc, 1 by lc, okay. So what you have to understand is this can be like reformatted. I will reformat it, okay. Let me first find out the omega l basically. So omega l, right, again the same equation only, just I have minus 1 by r here. So if I have minus 1 by r, right, the difference will be, this will be omega l whole square plus omega l divided by omega n into r divided by l, and this will be okay, this will be minus 1 by lc equals to 0. Will this be am I wrong, I am wrong. This, right, if I multiply by omega l, this will be omega l, r is there, rc only, okay, I was wrong. So again this omega l will be what, omega l will be minus of b 1 by rc plus minus b square 1 by rc whole square minus 4ac, this will be plus 4 lc divided by 2a, divided by 2a. So my omega l will be equals to minus 2 by RC plus minus whole under root 1 by 2 RC whole square plus 1 by LC. Okay, so sorry, this will be not 2 by 2 RC by 1 by 2 RC. So if I subtract, right, I will get the bandwidth. If I subtract the higher 3 dB frequency and the lower 3 dB frequency, I will get the bandwidth of the circuit. So bandwidth is defined as the omega H minus omega L. So it actually comes out to be 1 by RC. It actually comes out to be 1 by RC. Okay, so this is my bandwidth. So I can rewrite my formulas of omega L and omega H. Okay, I can rewrite it. Another important fact to note here is my bandwidth is not a function of inductor. So for a parallel resonance circuit, the bandwidth is just a function of capacitor and resistor. For a series resonance circuit, the bandwidth was function of inductor and resistor. So these things you have to keep in mind, but one formula will not change. That's why I told you to remember that formula. What is the formula? I can rewrite this thing. This is what? Bandwidth by 2. This is what? Bandwidth by 2. This is what? Omega naught whole square. So I can rewrite the same thing. Omega H will be equals to bandwidth by 2 plus bandwidth by 2 whole square plus omega naught square. Omega L is minus of bandwidth by 2 plus whole under root bandwidth by 2 whole square plus omega naught whole square. Okay, so ultimately, right, basically this formula is same as the series resonance circuit, right? But the main factor is this bandwidth is for a parallel circuit. So that is what you have to remember. So this formula remains same, but what is the bandwidth in a parallel resonance circuit, that you have to remember, right? That has changed. Although the resonant frequency has not changed, but the bandwidth has changed. So just keep that in mind. Another interesting fact, again the same formulas we will get, that is omega H into omega L you will get as omega naught whole square. So again I can say it is GM. Omega naught is the geometric mean of omega H and omega L. Same thing, right? Same thing. Nothing has changed. Again, now if I discuss about the angle, phase angle at 3 dB frequencies. So at phase angle of 3 dB frequency, if it is omega is equals to omega H. If omega is equals to omega H, basically, right, what is my angle? Angle is tan inverse omega C minus 1 by omega L divided by 1 by R. Okay. So now what I can comment? I can comment that omega C is like this is omega C minus this is the value, right? Basically omega C minus 1 by omega L either is equals to plus 1 by R or either equals to minus 1 by R, right? Either equals to plus 1 by R or minus 1 by R. If I replace here plus 1 by R, what will be this? This will be tan inverse 1, that is plus 45, and that makes sense because admittance angle is positive, it should be capacitive, which we have already discussed. If it is equals to plus 1 by R, it will be capacitive. So my magnitude at higher 3 dB frequency of admittance is what? It is 1 by R whole square, 1 by R whole square plus omega C minus 1 by omega L whole square, that is 2 by R square. So it is 2 by R square, like admittance whole square. So what will be the admittance? Admittance will be 2 by under root 2 by under root 2 by R. Admittance will be always under root 2 by R. Does not matter because sign does not matter. Either cases admittance will be, magnitude of the admittance will be under root 2 by R. Okay, but the sign angle phase matters, right? So phase of admittance in case of capacitive, it will be plus 45 degrees. Why? Because this also will be equals to plus 1 by R. If it is inductive, admittance will be tan inverse minus 1 by R divided by 1 by r. So it is tan inverse minus 1, so it will be minus 45 degrees. Okay, so you can find out the admittance angle as well. That is what is written in the summary. So in the summary, every single thing is written. What is the voltage, what is the like angle of the admittance, what is the angle of the voltage, currents, all those things are written. What is the power factor, unity, leading, all those things are written in the summary. Okay, in the summary. So I hope you have understood this very basic point basically. So admittance is what? Admittance is minimum at what frequency? At resonant frequency, because it is equals to 1 by r. After that, admittance increases. If admittance increases, what will happen? Admittance, like the voltage is equals to current by admittance. Admittance will increase, the voltage will decrease. So voltage also decreases. Okay, admittance increases, the voltage decreases basically. So I hope you have understood this point. So that is what is written over here. This is actually Z. Z. Okay. So like if you see the graph of admittance, admittance is very high at 0 frequency or infinity frequency. Why? If admittance, if omega is 0, omega 0 means omega L is 0. So like I am seeing inductance is short circuit. So what is the admittance? Admittance will be 1 by omega L. So 1 by 0 is infinity. That's why it is infinity, and in this region it will behave as a lagging circuit because it is inductive, and in this region it will behave as a leading circuit. This we have already I think previously discussed. Now we have discussed the angle as well, and this is the impedance basically. Impedance will be just the inverse of admittance. That's it. Okay. So this is the like not an exact phasor diagram, just a simple admittance diagram. Okay, some admittance diagram. This is not a phasor diagram because we are discussing at different frequencies. Okay, so at omega equals to omega naught, it will be minimum. Admittance will be minimum, that is 1 by r, not r. It will be 1 by r. I'm sorry. It will be 1 by r. At omega equals to omega h, it will be root 2 by r. Magnitude of the admittance will be root 2 by r, and angle will be plus 45. At omega equals to omega l, the magnitude of the admittance will be root 2 by r, and angle will be minus 45. Okay, so these are the admittance values basically. So I hope you understood. Now let's discuss like what does a parallel RLC circuit signifies. So a parallel RLC circuit is like a rejector circuit. Why it behaves as a rejector circuit, or it also behaves as an anti-resonance circuit? Now, like whenever a term is present, right, it is associated with some condition. So the condition is we are discussing about the currents. Okay, rejecting, it is rejecting the currents. What do I mean by rejection? So let's say I don't have any resistance. Okay, I have only this LNC. What is the resonant frequency? 1 by LC, 1 by 100 LC. That is the resonant frequency. And at resonant frequency, what happens basically is that my XL is equals to XC, correct? So if I see the input impedance, what is the equivalent? What is the equivalent input impedance? What is the equivalent input impedance? The equivalent input impedance is Z equals to J into XL into minus J into XC divided by J into XL minus XC. Okay, so this is the equivalent impedance basically. So I have told you that at resonance XL is equals to XC. That means this denominator will be 0. So this is finite. This will be some finite value divided by 0. So finite divided by 0 is infinity. So my input impedance at resonance is infinity, right? Z is tending towards infinity. So if it is tending towards infinity, will any current flow? So this particular impedance is telling me I have infinite input impedance. You cannot flow any current through me. Okay, but this obviously this current source is there. So ultimately, right, it is rejecting that this current source at for this particular frequency, because this is, it has infinite impedance only for this particular frequency. Other than that, the it has some finite input impedance and current will flow, no problem. But at resonant frequency, it is providing infinite impedance. So no current, it will not allow any current. Okay, so it is rejecting the current basically. That's why it is called as a rejector circuit. So this is the condition at resonant condition, at resonance. Okay, so whenever something is written, right, you have to understand with respect to what they are talking about rejector circuit, because I have seen many educators, they just say it is a rejector circuit, but it rejects what? Rejects what? You have to understand what it rejects. So it is rejecting the current basically. Got it? Anti-resonant, because in resonant circuit, in series RLC circuit, it was the maximum current. The circuit was allowing the maximum current. Here the circuit is not allowing any current. That's why anti-resonant is also sometimes referred for a parallel RLC circuit. Now let's do this quality factor derivation again. So same condition, right? Quality factor is 2 pi times maximum energy stored divided by power loss. Same, like I'm just simply using this formula. Okay, so again, what is the current? IR of t at resonance. So whatever we are discussing at resonance. Okay, so at resonance, what is the current through the resistor? It is simply like, if my input source, right, Is of t, Is of t equals to Im sin omega naught t, because it is at resonant frequency. So IR of t will be same as Is of t, correct? IR of t will be same as Is of t. So it will be at resonance basically, it will be equals to Im sin omega naught t. Okay, so now what is the voltage? What is the voltage? Voltage will be simply V into I into R, right? Voltage across the resistor will be current times the resistance. So it will be I into R, I of t, I of R into R. So this will be Im R sin omega naught t. Okay, so this is the voltage basically. Now what is the power dissipated across a resistor? What is the power dissipated across a resistor for a cycle? So power dissipated, or energy dissipated dissipated over a cycle, basically it will be power P of t into the integration of P of t from 0 to 2 pi of dt, correct? So what is the P of t? PR of t, the power dissipated across a resistor. So what is PR of t? PR of t is uh, I square R, you can write. So it will be I square t into R. So this will be Im square into sin square omega naught t into R. Into R. Okay, so this if I integrate, right, so energy loss, E loss, this will be 0 to 2 pi. Im square can go outside, Im square R can go outside, M square R, integration of sin square omega naught t dt. So this will be what? This will be basically half, right? Im square, and obviously omega naught will also be present into 1 by 2. Okay, this will be obviously there. Am I correct? Omega naught, yes. Okay, 0 to 2 pi, 0 to 2 pi sin square 1 by 2 over a complete pair is, yeah, over a complete pair is 0 to 2 pi, yeah, that's it. So I think if it is 0 to 2 pi, right, here this 2 pi will not be there actually. if I write this formula, it is energy loss over a cycle. Okay, so yeah, this is the value basically, Im square r divided by omega naught into half. Okay, now what is the energy stored basically? So this is the energy loss, this we have found out. What is the energy stored? For energy stored, I have to write down the expression. So this is the energy loss. I will not write EL, I will write E loss, else you will get confused. This will be E loss. What is the inductor current? So I know the voltage, right? I know the voltage across the inductor. Can I find out the current? Yes, I can. So the voltage across the inductor is same, right? It is a parallel circuit. So voltage will be same as this voltage. So voltage VL of t equals to Im into R sine omega naught t. Im into R sine omega naught t. Okay, so my current will be what? Current will be integration, right? 1 by L integration of this. So this will be 1 by L into Im into R will obviously be there, by omega naught will also be there, into cos minus cos, because integration of sine is minus cos omega naught t. Okay, this will be the integration basically. So this is equals to what? This is equals to minus, what is omega naught? Omega naught is 1 by under root LC, correct? So if it is 1 by under root LC, so this will get cancelled. So it will be R into under root C by L into Im minus Im into R omega naught under root C by L cos omega naught t. Okay, this is the current. So what is the energy stored? EL, E of L is half Li square, right? So it is half into Li square. So this will be Im square R square, L will get cancelled. This will be C cos square omega naught t. Okay, so this is the expression for the energy stored across the inductor. What about the capacitor? It is half CV square, right? Half CV square will be what? V, I already know what is the voltage. Voltage is this, right? Same, it is a parallel circuit, so voltage will be same, half CV square. So it will be half into C into V square. So it is Im square R square sine square omega naught t. So same, right? Whatever we have got in the series resonance circuit, same kind of thing we are getting. So what is the quality factor? Quality factor will be basically this energy stored by energy loss. So energy stored over a energy stored over a cycle basically. Now overall energy stored, right? What is the overall energy stored? Overall energy stored, not cycle, sorry. What is the overall energy stored? Overall energy stored is the E stored, because both capacitor and inductor are storing some energy at a particular instant. It will be EL plus EC. So this will be half Im square into C is obviously there, and it is sine square plus sine square omega naught t plus cos square omega naught t. So this will be half, basically this will be 1, right? So this will basically be half Im square R square C. So my quality factor is half Im square R square C divided by this quantity, right? This energy loss Im square R divided by omega naught, half Im square R divided by omega naught. So this will be Im will get cancelled, R will get cancelled. This is R C omega naught. Okay, R C omega naught, or this can be, it is correct, right? R C omega naught, yes. So this can be changed like this, that what is omega naught? 1 by under root LC. So this will be R under root C by L. Okay, it is R under root C by L, or you can write this as, it is basically it is YC, or I can write this as BC by G. G is the conductance, right? G is the conductance. Like this can be written as C omega, that is the susceptance, capacitive susceptance, divided by the conductance. Okay, like this you can write. There are many ways you can write this in terms of impedance as well. This will impedance, right? If I write, this will be R divided by XC. That is how you can write in terms of your impedance formula. Okay, both ways work. This is the energy oscillation, same whatever we have discussed in the previous case, right? Same thing is happening over here. Just this is a very important result for quality factor of a parallel circuit. So this is the important result for quality factor of a parallel circuit. Okay, so if you notice something, if you remember a few things, what you can remember is that the quality factor is actually of a series circuit was quality factor of a series circuit is 1 by R under root L by C. Quality factor of a parallel circuit equals to R under root C by L. So basically they are all inverse of each other, right? So what I can say is quality factor of parallel circuit is equals to 1 by quality factor of series circuit. Okay, so we can write this quality factor of a parallel circuit in more ways, like it can be written as the current ratio. So current across the inductor divided by current across the resistor, this you can write. Okay, so why can I write it? Because I know this is equals to what? It is equals to C omega by 1 by R, or BC by G. It is equals to BC by G, right? The capacitive susceptance divided by the admittance or the conductance basically. Okay, so what I can say is, if I multiply voltage on both sides, voltage into BC, because voltage is common, it is a parallel circuit, so voltage will be common, right? So if I just like bring the circuit, so voltage is common basically, right? Voltage is common. So if I multiply voltage, what is this quantity? This is current, right? What is current? This voltage times the conductance of this, so it is current of the resistor. So this will be IR IR divided by I, sorry, not IR, sorry, this will be IC divided by IL, as in like the, not exactly, this is magnitude of IC divided by, not IL, sorry, IR, magnitude of IR. So as at resonance, the magnitude of IC is equals to magnitude of IL, right? That we already know. At resonance they cancel each other out. So this can be also written as magnitude of IL divided by magnitude of IR. Okay, same thing only, it will work. You can also write this as, it was what, omega naught RC, right? It was omega naught RC. Okay, I know what is omega naught C. It is 1 by XC, and XC is equals to XL. So this can be also written as R by XL, R by omega naught L. This is also another way to write it, or this can also be written as, I will write here, my quality factor can also be written as R by XL, or it can be written as R by XC. Okay, so both way works basically, does not matter. Like there are numerous formulas, don't have to remember everything, just understand one and then you can derive all the other results. Okay, so yeah, now let's come to the zeta basically. What is the relationship between zeta and the quality factor? So if you don't know about zeta, you can ignore the fact. If you don't understand Laplace, you can ignore this next 5 to 10 minutes. So if I just bring this circuit, right, okay, so this will be SL, this will be 1 by SC. Okay, so now what I can say is that current division is happening, right? Current division is happening. So what is my IR is equals to, I don't care about the numerator, I just care about the denominator, that is the characteristics equation. So my IR is current division, right? It is I of S into this R divided by all the other values. So this, am I correct? I don't think I'm correct, because this voltage is there. So what we can do, right? Voltage is same. Okay, no, this is not correct. So if I get the conductance, then right, then it will be very simple. If I get the conductance, yes, if I know the conductance, it will be what, like what is my uh, current equals to conductance time voltage. So this voltage is common between all of them. So what is the value of the voltage at resonance? The value of the voltage at resonance is simply the current into resistor only. Okay, no, I'm not trying that. I'm trying something else. Let me think. This is one where, okay, admittance is there. Okay, okay. Okay, let's apply a nodal here. This is the V value, right? So V divided by R plus V divided by SL plus V into SC minus I equals to 0. So V into 1 by R plus 1 by SL plus SC equals to I. So from here, right, I can directly write the voltage in terms of current. So what will be the voltage? Voltage will be I divided by I into SL, this right, R will be multiplied here, SL will be multiplied here, R will be multiplied here, both S square LCR everything will be multiplied divided by, okay, not this will be in the bottom, this will be at the top, this will be S R L, yes. So from here my characteristic equation is S square plus S divided by RC plus R will get cancelled, 1 divided by LC equals to 0. I'm just talking about the characteristics equation. So here what you can write your value of zeta. So your omega n is again what, omega n square, because your standard equation is what, s square plus 2 zeta omega n s plus omega n square. So for the students who don't understand this control system, right, they can ignore this. You will revisit this once you have studied control systems. So this is s square plus s by rc plus 1 by lc. So this will be to omega n. So omega n is 1 by under root lc, and your zeta is what, 2 zeta omega n is 2 zeta omega n is 1 by rc, and your omega n is 1 by under root lc. So your zeta is equals to under root L will go there, R will still be here by 2 under root, and this C will still be there, L. Okay, so this L under root L by C, right? Actually, this under root L by C has units. So I will tell you the trick as well, how you can remember the quality factor. I will just tell you in a second. So what I observe is this is basically equals to my quality factor, but in inverse, right? And multiplied by 2. If I multiply this by 2 and take the inverse of this, this will be equals to my quality factor. This will be equals to my quality factor, which was happening previously as well. Okay, which I was getting previously as well. Okay, so that is the interesting fact. This relationship does not change. But remember, this zeta is for what? This zeta is for a parallel circuit. This zeta is for a parallel circuit. Zeta for the circuit also changes, right? That's why you feel like the relation is constant, but no, the zeta has changed. Okay, so this kind of relation we derive in the series circuit as well. Now, how can you remember this? So this you will study in power systems and many other places, that under root L by C is actually the characteristics impedance. Okay, so how do you remember this quality factor formula? So quality factor is here, right? This formula, quality factor of a series and quality factor of the parallel circuit. So I have already told you that under root L by C is the unit of impedance, because it is the characteristics impedance, and my quality factor is a unitless number. So if I am writing anywhere under root L by C, I have to cancel the units. So if it is under root L by C, then that means I have currently a unit of ohm. How will I cancel the unit? By dividing by R, because R has unit of ohm. So ohm will cancel ohm. Ultimately, the quantity I will get as unitless. So this is how you will remember. So you remember for quality factor, for series circuit, the quality factor, it has the term under root L by C. So you got the term. Now, do I need to divide by R or multiply by R? Just check with a unit. Check with a unit, because it is under root L by C. So currently the unit is ohm. So I have to divide by R so that the unit becomes unitless. Ohm cancels ohm. What about the parallel circuit? What about the parallel circuit? So for the parallel circuit, this unit has ohms, right? So again, for parallel, you remember for series, okay? Remember for series. Then for parallel, you know, it will be just opposite. So if it is just opposite, that means everything will be inverse, right? So remember for series, and for parallel, just remember this relationship, that parallel quality factor will be the inverse of the series quality factor. That's it. Or you can make your own way as well, that is up to you, but this is how I used to remember. I used to remember the series quality factor 1 by R under L by C. Then from there I used to go to the parallel circuit. And how to remember the 3 dB cutoff frequencies, that also I have explained, right? You always remember the 3 dB cutoff frequencies with the help of bandwidth. Also another result of quality factor which will never change, that is quality factor, right, will always be equals to omega naught resonant frequency divided by bandwidth. So in this case, what is omega naught? Omega naught is 1 by under root LC, that does not change. But what is the bandwidth? The bandwidth has changed now. Bandwidth is RC. Bandwidth is omega naught RC. Bandwidth is RC. Yes, bandwidth is RC. Or 1 by RC, sorry. Bandwidth is 1 by RC, right? Yes. bandwidth, yeah, bandwidth is 1 by RC. So how do I remember bandwidth? So I know bandwidth, right? For a first order circuit, bandwidth is actually equals to inverse of time constant, tau, basically time constant for a first order circuit. Okay, this is just I'm talking about high level things here. So for a first order circuit, the bandwidth is equals to time constant, 1 by time constant, because bandwidth has a unit of what? Bandwidth is frequency, right? And this time constant has a unit of second. So 1 by second will be unit of frequency. So that's how I used to remember that bandwidth is equals to 1 by time constant. Okay. So if it is 1 by time constant, you can directly write here, right? That what is the time constant? I remember that in a series circuit, the time constant is the bandwidth is a function of inductance. And what is the time constant? Just simply remember for a RL circuit, what is the time constant? L by R. So you will write that there. You write the inverse, basically you write the R by L, right? And L will go above basically. Okay, that's how I hope you remember. For a parallel circuit, you remember, okay, you remember for a parallel circuit, my bandwidth, for a parallel circuit, my bandwidth is a function of capacitor. It is not a function of inductor. It is a function of capacitor and resistor. So if you remember that and you know that bandwidth is 1 by time constant, so what is the time constant for a RC circuit? It is RC. For a RC circuit, the time constant is, so yeah, time constant is RC, right? So I have to take the inverse. So it will be 1 by RC. So from here you first write the tau is RC, and then you take the inverse of the tau. So that's how I used to remember the bandwidth for different circuits. So remember, for a parallel circuit, my bandwidth will not be a function of inductor. For a series circuit, the bandwidth will not be a function of capacitor. Okay. And of course, if you want to, like, this is in terms of radian per second. If you want to write in hertz, what you will do? You will divide by 2 pi RC. If I divide by 2 pi RC, it will be in seconds. Hertz per second, right? Hertz, it will be in hertz. Okay. So these few things you should keep in mind. And of course, again, the same thing will happen. If you notice, right, if you observe your inductor current at resonance, I'm talking about at resonance, you can derive this, that this is the homework for you. You will observe that your inductor current will be equals to minus of J Q the resistor current. Why minus J? Because current lags the voltage for a inductive circuit, and your capacitor current will be, this is in phasor, will be plus J Q of resistor current. Okay. So yeah, of course you do understand that if my Q is very high, greater than 1, then my magnitude of IL will be very greater than the magnitude of IR, basically the magnitude of IR. Okay. So yeah, or IR is what? At resonance, IR is simply equals to magnitude of I only, the supply current. Okay, so these things you should keep in mind. So like I have summarized all the, I think most of the points whatever I have discussed, I have summarized. So again, one more thing, what is the cutoff frequency? Cutoff frequency omega h equals to minus plus bandwidth by 2. This formula will be constant, right? But this is the parallel bandwidth. This you have to remember. Omega h parallel. I am talking about the parallel resonance circuit. It will be parallel bandwidth by 2 plus under root parallel bandwidth by 2 whole square plus r square. Not r square, sorry, omega naught whole square. Omega naught is same for parallel and series RLC circuit, so it does not matter. What about the lower 3 dB frequency? Everything will be same. Basically, everything will be same. here, right, there will be a negative sign here, that's it, because it is a lower 3 dB frequency. And of course, lower 3 dB frequency, my circuit will behave as what? My circuit will behave as inductive, because the inductive susceptance will be the lowest, so more current will flow through the inductor, so that's why it will behave as an inductive circuit. And for omega greater than omega naught, it will behave as a capacitive circuit, because then the capacitive susceptance will be lower, sorry, not lower, capacitive susceptance will be higher. Why? Because your BC will be higher here, BC will be greater than BL, and here my BL will be greater than BC, whose susceptance is more the current will flow. Okay, or opposite, you can understand that the impedance or the capacitive reactance will be more here, that's why less current will flow through the capacitor and more current will flow through the inductor. Here the inductive reactance will be more, hence less current will flow through the inductor and more current will flow through the capacitor. If you are not able to understand, please rewind and try to write it down by yourself and just see what am I speaking. Write down the statement, then you will understand. Okay, so these are the key differences between series and parallel resonance circuit. Omega naught is same, quality factor will be different. Here it will be omega naught L by R, it will be R by omega naught L, or this can be written as R by omega naught C, not C, sorry, yeah, R by omega naught C also. This can be no, this cannot be written R by omega naught C, this can be written as R by XC basically, and XC is 1 by omega naught C. So yeah, these are the conditions basically. Maximum impedance is minimum here, Z equals to R, and the impedance is maximum L by C or RC. Impedance, actually we don't discuss about when is the maximum impedance. The admittance is minimum, admittance is minimum at R. So here, right, here also the impedance will be maximum only, right? Impedance will be maximum only, this will not be R basically, because at resonance what is happening, the other two reactive elements are providing infinite impedance, hence they are out of the action, so only the resistance is there which is providing the maximum impedance. So impedance will be maximum here, Z equals to R. Here voltage magnification will happen, here the current magnification will happen in parallel resonance circuit. Bandwidth, what is the bandwidth? Omega naught by Q, here also same formula. Bandwidth depends on capacitor, no, in this series RLC, right, bandwidth depends on the inductor basically, not the capacitor, sorry. And in the parallel RLC, bandwidth depends on the capacitor. Okay, it is, think, okay, this is different, this should be here, right, sorry. Okay, okay, yeah, now it is fine. So here bandwidth depends on inductor, and here bandwidth depends on capacitor. Yes, now it is fine. Okay, it behaves as a acceptor circuit, it allows all the frequencies, it rejects that specific resonant frequency, right, no current flows if we have concluded, like we have already concluded that thing, right. So yeah, these were the few things that I wanted to like discuss. So few more key points are there that I will discuss, and then we will wrap up this lecture basically. So these are the key differences between a series and parallel RLC. Series RLC is used for voltage magnification, parallel RLC is used for current magnification. It acts as a rejector, so meaning it blocks signals at resonant frequency, it passes signals at resonance frequency. Bandwidth and quality factor are already discussed, these are the formulas that we have already discussed. I don't think we need to discuss this again, this already have been discussed, right, so I don't think this page is required. So yeah, parallel RLC cancels each other out, you can see, you can read, everything is like same, only whatever we discussed that is written over here. So with this we finish our parallel resonance circuit, and in the next lecture we will try to do all the assignment questions that are in this chapter, and that will finish the chapter of resonance, the most important chapter of AC analysis. Thank you for watching, and I will see you in the next lecture. Until then, happy learning.